Hey there, hi, this is Angie over at Angie's Beyond the Lecture, and today's discussion is going to cover the concept of the mole in chemistry. So some of you as chemistry students or just, people off the street may have asked yourselves, okay, so how do scientists measure a large quantity of atoms? Or how do they measure basically very, very tiny atoms or molecules that are super duper small? How do they measure these and basically scale them up? Okay, so think about this. I mean, we know molecules are composed of atoms. They're itty bitty bitty, right? So scientists aren't in a lab like picking up individual atoms, right, with itty bitty molecular atom sized tweezers. Okay, we need to scale things up, and this is where the mole concept comes in chemistry. And some time ago, there was someone by the name of Avogadro who contributed very much in chemistry and science in general. And scientists came up with or agreed upon this Avogadro's number, or the concept of a mole, and stating that a mole of any substance, okay, whether it's an element or a molecule, say like maybe CO2, something like that, NaCl, right? Anything, whether it's molecular, ionic, maybe just pure gas like argon, again, our good old friend argon. So basically scientists agreed on Avogadro's number as 6.022 times 10 to the 23rd. We call them representative particles. We can also, and that's just a generic term, but we can also represent that as atoms, molecules, or formula units. Now, formula units right here, that actually pertains to the ionic compounds. Okay, so that's your ionic compounds right there. So molecules refer to covalent, formula units refer to ionic compounds. So molecules, covalent compounds, formula units, ionic compounds. We do have this definition of the mole, okay, and we can also equate it to, for instance, it's similar in nature to like a dozen. Okay, so if I go to the bakery and order a dozen donuts, I know I'm getting 12. Okay, so if I'm working with a mole's worth of substance, I know I have Avogadro's number right there, right? The 6.022 times 10 to the 23 particles. 10 to the 23 is humongous. I believe it's like hexillion if you look it up. If you actually look up moles, what moles represent online. So it's a humongous number. But again, these are very, very tiny atoms, right? So the radius of an atom is like in the picometer scale, right? It's 10 to the negative 12, 10 to the negative 15 meters, in distance. So we're talking, of course, very, very small particles here. So of course, we're going to need a lot to fill up 1 mole that's practical for us to use, for instance, in the lab. So we can, basically, and that kind of takes us into calculating molar mass. Okay, so every element that's represented on the periodic table has its own distinct mass. And if we go over to, for instance, carbon, I already have carbon highlighted or, in blue, but, carbon is a very, common element in nature. And we know that it's 12 grams per mole. Okay, 12 grams per mole. So that's what we call molar mass. And each individual element has its own molar mass. So if I have, for instance, 1 mole of magnesium metal right here on the left, I have approximately 24 grams. So when you're in your chemistry course, some teachers will say, just round to the nearest whole gram when you do your calculations. Some want you to use, the entire decimal. So just be aware of that. It depends on the teacher or professor when using those values. So back to the review sheet here. So we have steps for molar mass here. Yeah. So we have, for instance, water, water's everywhere, right? So we have the formula for water. So to calculate that molar mass of that particular compound, when it's more than 1 element, okay, we just add it all together. it's an additive process. All right. So if we take, for instance, two hydrogens at, and I'll just highlight this here. If we take two hydrogens at the 1.008, or you could probably use one, we have just over 2 grams per mole of hydrogen that we have there. Remember, we do have two for every water molecule. And then we have that one oxygen. That oxygen weighs in at 16 grams per 1 mole. Some periodic tables have 15.999, but I think most teachers will just let you use 16 for that. So when we add them all together here, we're going to have 2 for 2.016 plus 16 to give us just over 18 grams per mole. All right. So remember, it's always additive. This is a simple example here. I can attach additional examples. And your teacher or professor, I'm sure, is going to take you through a lot of those examples. So moving on down. So we have our mole. We can, of course, given moles, we can determine how many particles or atoms or molecules that we have. For example, we can convert moles to particles, and then we can go in reverse. We can convert particles back to moles. And then I'm just going to skim on down here to our additional examples. We also have a definition that at standard temperature and pressure, that is 1 mole of any gas occupies 22.4 liters. Standard temperature and pressure is actually, I should have written that down, that's 0 degrees Celsius and 1 atmosphere. And 1 atmosphere is typically your atmospheric pressure at sea level. Okay, so scientists agree that at STP, we have a temperature of 0 degrees Celsius and 1 atmospheric pressure. So we can determine that 1 mole of any gas, it doesn't matter what kind of gas it is. It could be argon, hydrogen. In our example, we're doing oxygen. It doesn't matter. The volume it will occupy is always going to be the 22.4 liters of gas. Okay, so, and I'll circle back and we'll do these examples. You can also go from liters back to moles. So notice you can go forwards. You can take moles out to grams of substance or liters of gas, and you can always go back to moles from grams or liters. Here, I conveniently, just for these two examples, I went ahead and you have the calculation for that. So there's no need to go and add it up. All right, so example 3, we just have 2 more examples here. We have moles to grams, and then we have grams to moles. So we can figure out if we have 5 moles of any kind of substance, and here we're talking about sodium chloride, we can go ahead and figure out how much we have in mass or grams, and when vice versa. I can be given the total number of grams and go back to moles, okay? So I would say number 3 is the most common, the common conversion you'll use in chemistry. And of course, I'm going to take us back up to number 2. We have an entire unit dedicated to gas. So you'll see more of these problems in the gas unit, or what we call gas laws, okay? And then, of course, we have moles to particles, particles to moles. So I would say out of those 3, this is the, you still have to know the concept, but you're not going to use it quite as much. So in this space here, I'm just going to go ahead and calculate if I have, I got my little trusty calculator here. Okay, so if I have 3.5 moles of H2O, always put your units in. I know 1 mole of anything, in this case 1 mole of H2O, has 6.022 times 10 to the 23, and we'll say molecules. H2O is a covalent, it's a covalent molecule, or compound, sorry, compound. Okay, so we'll have, I'll just take it out to 2 sig figs. All right, there you go. So we have 2.1 times 10 to the 24 H2O molecules is your answer. Yeah. So be comfortable with large numbers there, right? 10 to the 24. And then we can go backwards. We can say, all right, if we have 4.5 atoms, okay. So this is a straight up element. So we would just say atoms of aluminum. And one thing I didn't emphasize here in the last problem in example one is that you should cancel these units after you apply your ratio. You should cancel them before you do the final calculation, because then you'll be certain that your original unit cancels and that your end result would be molecules of H2O. Make sure and have that substance there, right? This is what we're looking for, right? That should be the only unit left standing when you're doing these problems. So when I go back to example two, we have this certain number of atoms, and notice we're going to divide instead of multiply. So we're just going to take our given quantity, the 4.5, 10 to the 24th, and we'll just divide out by Avogadro, and we'll get roughly, just say 7.5 moles. Perfect, okay. So first one we divide, the second one we are, the first one we're going to multiply, the second one we're going to divide. So you multiply to go out from moles, you divide to go back in. And I'm going to show you a diagram just to emphasize this here at the end. All right, so liters of gas at STP, and remember it's 0 degrees Celsius, 1 atmosphere for pressure, and this is our constant, right? That's our constant value. 1 mole of any gas is going to have that volume. So when we take 2.8 moles O2, and I know 1 mole of O2 or any gas. Okay. All right, so we're just basically taking 2.8 times 22.4. There we go, 62.7. Again, I'm not really tending to significant figures, and that's okay. This is just, we're trying to follow the math and the structure of everything that we're doing. Now, we're going to go backwards given a particular volume of gas at STP. This is carbon dioxide. I know 1 mole. By the way, this is typically how these I hit erase. This is typically how these questions are arranged. How many moles of carbon? How many grams of carbon? Right? What volume do you have? They're pretty short. They're pretty short and to the point. Okay. So here we have 44.8. We'll divide out by the 22.4. Oh, that's lovely. It's 2. 2 moles. You have exactly 2 moles of CO2. Okay, and we're getting to the end here. Just a couple more of examples, and I'll show that diagram here. So we have, for this example, we have 5.0. I probably should tend to my sig figs, but again, I'm just trying to do the math here. 1 mole of NaCl has a mass of 58.44 grams, okay? So notice grams per mole, right? Grams per mole there. So, oh, yeah, grams of NaCl. Okay, we will cross those off. And, we're just taking 5 moles times 58.44. I'm just going to put 209 to 2. Okay. So if I have 5 moles of NaCl, that's our sodium chloride, I know I have 292 grams of salt. Our last example here, we're going to have 100 grams of sulfuric acid. And we know, we know 1 mole on the top. A good tip here too is that, when you put your quantity down, the first thing you should probably do is put your grams wherever grams is. So for instance, molar mass of the H2SO4 is 98.09 grams. Okay, so then immediately that'll go on the bottom. The grams will go on the bottom, so you can just cancel them out right away. And then of course where else do you put the mole, right? Well, you can't go wrong here. The mole will either go on the top or the bottom, but what's left, it's the top. So we're taking 100 and dividing out by 98.09. So it's almost, it's almost a 1-to-1 ratio. I guess it's looking to be maybe just over a mole, 1.019. I mean, they gave us 4 sig figs. I mean, if we're going to answer this appropriately, 4 sig figs would be 1.019 moles of H2SO4. And just to reiterate, I really didn't tend to the sig figs. I just rounded to what seemed right. And we'll go over sig figs here in a different video. But at the end here, so we just have some key takeaways. Make sure you understand the mole is that assigned quantity. It's never going to change. It's always going to be 6.022 times 10 to the 23rd. And then we also have 1 mole of gas at standard temperature and pressure conditions will occupy 22.4 liters in volume. And then we know 1 mole of anything is just its molar mass, and that's dictated by the periodic table. So that's going to be your friend. Yay. And use dimensional analysis. So this right up here, hi, don't erase for me. This right up here, this is called dimensional analysis. And I will do another video that covers dimensional analysis in more depth. But I hope you found this helpful. And again, if you actually maybe search for a mole diagram, you're probably going to see something like this. Okay, there's the central mole. Mole is in the center, right? And you might see there's mass, there's liters of gas. That's at STP. That's the quantifier or the qualifier here. It has to be STP. And then we also have, number of particles. And I won't write those all out again, but we know those are atoms, molecules, formula units, et cetera, et cetera. So remember, you multiply by molar mass to get just the mass of what you have in grams, right? I'll just put grams there. Actually, I don't want to confuse that with gas. I'll put grams. I'll spell it out. Okay, so you take number of moles, multiply out by your molar mass to get how many grams you have of something, whatever you're being asked. And to go from mass back to moles, you just divide. And then there's our constant mole. 22.41, or I think it's 22.4, but you can actually say 22.41 there for your moles, or sorry, liters of gas. And then, so when you take moles out to liters, you're just multiplying, and then taking liters of gas back to moles, you're dividing. We've already seen that. And then one final stop here on the mole diagram is number of particles. So we multiply out by Avogadro's number to go from moles out to particles, and then we just divide. This is just like a shortcut diagram, but if you do your dimensional analysis correctly, I mean, the numbers will wash out, and you'll see multiply to go out, divide to go back in. You almost got to repeat that in your mind a few times and it'll stick. So again, thank you for watching this video, and I'll go ahead and link out the next video will be additional dimensional analysis problems. So not just moles, but like say feet to inches or grams to pounds. I mean, just for additional practice and review on dimensional analysis, I think is great